Let's start with the problem of trying to estimate the value of some parameter. If we call the parameter theta, then maybe we calculate some statistic t, and we think that t is a good estimate of theta, that in general t should equal theta or be close to theta, ideally. If I'm using t to estimate theta, then the bias associated with this, written as the bias of t for theta, is the expected value of t minus theta. Now, these are terms which I'm sure you hear in everyday life as well as in statistics, but we have this idea of an estimator either being biased or unbiased. So perhaps unsurprisingly, an unbiased estimator has a bias of 0, and if the bias is non-zero, then we can say that t would be a biased estimator of the value of theta. So let's give another example. If x is a random variable, all I'm going to assume now is that it has finite mean, mu, and finite variance, sigma squared. We've already seen the method of moments. If not, please go back and see the video on the method of moments. But it's a way of estimating parameters by matching population moments to their equivalent sample moments. So here, for example, if I calculate the sample mean, which I'm calling S1 here, I would do that by adding up n realizations of x, x1 plus x2 plus x3, dot, 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 up to xn, and dividing by n. So I'll get x bar, the sample mean. So the method of moments would say that if the first sample mean is x bar, then the population mean mu, I would estimate mu, which I've written mu hat mm to say it's my estimate of mu, using the method of moments, would be x bar. Similarly, the second central sample moment, so adding up each observation xi's distance away from x bar, squaring those, adding those, and dividing by n, will give me the second central sample moment, which should be somehow useful as an estimator of the second central population moment, or the population variance. So if I estimate sigma squared by the second central sample moment, then I would get sigma squared hat by the method of moments is the second central sample moment. Now, you may already know this, but one of those estimators is unbiased and the other is not. Now, I hope it's easy to see that the method of moments applied to the first moment gives an unbiased estimator for mu, because every time I take a sample, a random sample, I'll get a random value, but the expected value of the first sample moment is the expected value of x bar, which is the expected value of 1 over n times the sum of my xi's, which I can pull the 1 over n term out the front, so I get 1 over n times the expectation of the sum of my xi's. Each xi has expectation mu, so the sum of n things, each equal to mu, will give me n mu. So the expected value of the first sample moment is the first population moment. What it does tell me is that using the method of moments applied to the first moment, I have an unbiased estimator for the population mean. Well, I said one of these two estimators was biased and one was unbiased, and we've already seen that the estimator for the mean was unbiased. So let's see what we get for the estimator for the variance. Well, the expected value of 1 over n times the sum of the squared distances between each observation and x bar. Before I work that out, I'm going to expand that. Even though there's two terms, xi minus x bar squared, I've added in a minus mu and a, well, minus minus mu. So I haven't changed the value, but now I can expand that. And when I expand that, what I'll start to see is the difference between the first term minus the second term squared will be the first term squared plus the second term squared minus twice the product. Now at this point I can say that x bar minus mu is going to be equal to 1 over n times the sum of the xi's minus mu by definition, because x bar is the sum of the xi's over n. So when I start to substitute that in there, then my last term in particular simplifies quite readily. And of course, when I simplify that further by combining the last two terms here, then what we obtain, going fully through this, is that the expected value of the second central sample moment is not going to be sigma squared. My leading term is sigma squared, but I'm also subtracting away something which is sigma squared over n. In other words, the second central sample moment is going to give me a biased estimator of the population variance. And it's not just biased, it's always going to give me an underestimate of it, because n is always positive, and I'm subtracting away minus sigma squared over n. So I'm always going to underestimate the population variance if I just use the second central sample moment. And the reason for that is I've got this sort of circular logic that I'm using the same observations to try and work out how much spread, how much variation there is in the data, and where the mean of that is, where the middle of that is. So if I get a really unusually large or unusually small observation, it will also pull the mean in its outlierish direction, whether that's up or down. So when I observe a very large deviation, it also pulls the mean in that direction, which makes me underestimate just how large or how anomalous that observation is. So this is why I can correct for this because I know that the variance, that the factor by which I would be underestimating it is this sort of n minus 1 over n term. So I can correct for it by multiplying by n over n minus 1, where n is the number of observations. And this is why we sometimes see calculating a standard deviation or estimating sigma squared for population. If I'm using a sample, I will often divide by n minus 1 instead of by n to get the unbiased estimator.